For this part of the class, a homework problem after we did the ring of charge was to find the field at the center of the ring. Where is the field of maximum? What is that maximum field? And what is the field once we get really far away? So let's start with part A. What is the field at the center of the ring? We'll begin with the result from the electric field that we found in class. So part A, E at the center means E where x equals 0, because at the center of the ring is at the origin, so x equals 0 right there at the center. So E at x equals 0 equals k times 0 times q over a squared plus 0 squared to the 3 over 2, I equals 0, which is exactly what you would expect from the symmetry of the problem. Part B, where is the field a maximum? So for max-min problems, we know that at a maximum or a minimum, the derivative of the expression is going to be equal to 0. So the maximum occurs where dE dx equals 0. So we need to take the derivative here and set that equal to 0. So we're doing d by dx of k times x times q over a squared plus x squared to the 3 over 2. We're going to do the derivative of this guy. We can take our constants out front, so we have k times q d by dx of x over a squared plus x squared to the 3 over 2. We're going to do our derivative. I always use the product rule. So we get k times q times the derivative of the first term, derivative of x is just 1, times the second term, a squared plus x squared to the 3 over 2. And then we have to add it to plus this times the derivative of this. So we have x, the derivative of this here is minus 3 over 2 times the argument, a squared plus x squared. The exponent is down by 1, so it's to the minus 5 over 2, times the derivative of what's inside, 2 times x. So there's our derivative. Let's simplify this just a tiny bit, and that should be to the minus 3 halves there. So we can write it out this way, kq 1 over a squared plus x squared to the 3 over 2 minus 3 times x squared, because we have an x times an x. The 2 over the 2 here cancels. X squared plus a squared to the 5 over 2. So there's a slightly nicer form for our derivative. We know that we want this to be equal to 0. Let's find a common denominator first. We'll make it a little easier to figure out. K times q outside of a squared, oh my goodness, outside of x squared plus a squared over a squared plus x squared to the 5 over 2 minus 3x squared over x squared plus a squared to the 5 over 2. Now we have a common denominator, k times q, so we can add up the numerator. X squared minus 3x squared is minus 2x squared. And then we have a squared plus x squared to the 5 over 2 on the bottom. We know that for a maximum, this whole guy is going to be equal to 0. So that means this expression is going to be equal to 0. So our first answer is, let's just write that part out again. Minus 2x squared plus a squared over a squared plus x squared to the 5 over 2 equals 0. So we have two solutions for this that we can find. The first, if x equals infinity, this whole expression will be equal to 0. That's kind of a boring answer, and that would in fact be a minimum instead of a maximum. And now our next case where we can get the whole expression equals 0 is if our numerator equals 0, minus 2x squared plus a squared equals 0. That will give us x equals a over root 2. So this is where our electric field is a maximum, where x is equal to the radius divided by root 2. The next part said find the value of the electric field, so we'll just plug this in for our x value. So electric field is equal to k times x times q over a squared plus x squared to the 3 over 2. That's in the x direction. Plug in this for our a. We get k times a over root 2 times q. A squared plus x squared. X squared is going to be a squared over 2. That's to the power of 3 over 2. It's in the x direction. We can simplify that a little bit. So we get k times a over root 2 times q. Over on the bottom we have a squared plus a squared over 2, so we get 3a squared over 2 on the bottom. That's to the exponent of 3 over 2. And in the x direction, of course. So now we have, let's multiply out this bottom term using our exponent. So we get k times a over root 2 times q in the x direction. On the bottom, we have 3 to the power of 3 over 2 is the square root of 27. So 27 is 3 cubed. Square root is your power of 1/2. A squared to the 3 over 2 is a cubed. 2 to the power of 3 over 2 is 2 root 2 or root 8. So this a goes to an a squared down here. Root 2 cancels. And we are left with our electric field equals k times 2 times q over root 27a squared in the x direction. In the last part, what happens if x is really big, if your distance away is further? So we're kind of getting closer to that big value of x. So if x is much greater than a, part C, our electric field E equals k times x times q over a squared plus x squared to the 3 over 2 I. If x is much larger, then a squared plus x squared is about equal to x squared. Okay, so if x is really big, this a squared doesn't have much contribution. What that would mean is that a squared plus x squared to the 3 over 2 is about equal to x squared to the 3 over 2, which is equal to x cubed. So let's fill this in for our denominator and see what we get for our electric field. So the electric field would be approximately equal to k times x times q over x cubed. In the x direction, we have x on top, x cubed on the bottom, so our final result would be k times q times x, k times q times x squared in the x direction. So if we get pretty far away from our ring so that the diameter of the ring is negligible compared to where we are, it just looks like a point charge with magnitude of charge q.